Okay, hopefully you see the screen, right? Okay, so guys, in the previous class, in general statement, we dealt with the block diagram, including the controller, then the plant G, the output of the system being sensed by sensor H, and to be compared with inputs X, Y, E, and U. Remember? And we derive the closed loop transfer function y over x was Cg in 1 plus Cgh. And the open loop transfer function in general statement, we got, if this is B over E, which was Cgh. Then I simplified the block diagram by assuming that our sensor is ideal. So H, transfer function of the sensor, is 1, and there is no controller, only unity feedback plant, and the Y being compared with the input. Still, this is E, error signal. So by doing that, y over x closed loop transfer function was G, 1 plus G. Okay, you see that we removed C from here and H from here, and C from here, G, 1 plus G. And the open loop transfer function gonna be G, obviously, by removing C from here and the H from here. Okay? And I told you, and we went over a problem that theta double dot, our pendulum problem, plus omega n squared theta was omega n squared tau. If you have in your notes, after applying the Laplace transform, here we go, and assuming that the theta at angle 0 is 0, and the angular velocity of the pendulum at 0 is 0, starting from rest, we got theta of s, output over input, closed loop transfer function was omega squared, and s squared plus omega n squared. Hopefully recording, yeah. So when I plotted this, and I'm gonna do eventually today in the next class. So this is the, from here, I taught you that for finding the open loop transfer function, this is equal to G plus 1 plus G, see here. And we found that the open loop transfer function that you have in your notes is omega squared over s squared. So this is the output of theta of s. This is the input to the system, and being compared with the inputs. And this gives you the error signal in the frequency domain. And in the previous class, I taught you that the open loop transfer function already has what? You tell me. Has what? Two what? Yeah, two integrator. So two integrator means two I controller. And I told you that I gave a big picture before going in detail toward the end of the semester. I controller function is to make error signal to 0, E of t to 0. Okay. Example is that you want to set the temperature of this room to 80 degrees Fahrenheit, and the current temperature is 45. By adding the I controller, if you have a steady state error signal, this is going to make that happen for you. I controller. Simply speaking, 1 over s integrator make that happen for you. Okay? Clear? So now the question is that how we calculate E of s. how we calculate E of S. I'm going to stick to this problem, and then I'm going to move to MATLAB today. Okay. So by doing that, did I teach you the final value theorem? Yes, I don't think so. That's right, final value theorem. So yeah, so it's gonna be final value theorem. Final value theorem. So guys, with this general block diagram, see G of S. I'm dropping S because we know we are in the frequency domain. X and Y, general statement. And this is E. You see that E of S is X minus Y. See, X minus Y. We are not blind. And we see that based on whatever I taught you, Y is GE. GE. See what I'm saying? So if you implement Y from here to here, your error signal is going to be input minus GE. So on the other hand, if you move this to the left hand side and factor out E, it's going to be 1 plus G open loop transfer function. And in X, obviously all of them, they are in the frequency domain S. So E of S, I'm writing here, gonna be input to the system X of S plus G of S. Bingo. So what final value of theorem says? It says if you have a given function of Y of S, any function, say I'm just changing the name, Z of S. Z of S. So Z of t steady state value gonna be limit of S Z of S when S goes to 0. Okay guys, the name of this is the final value theorem. It's interesting, it says steady state value, guys. Steady state. This is for steady state value. If I want to plot it here, if this is Z and this is T, so suppose that you have this. Okay, we have such a graph. We name this vanishing, as I told you, vanishing dynamics. We name it transient phase. Transient. So we're going to go on over the method of transient phase. And we're going to name this steady state because it's a final value. See, it's steady state. So this is steady state. SS. SS. Can you give me why this limit when S goes to 0 gives you final value theorem by using this graph? Can you do the brainstorming for me? Why S must goes to 0 when time goes to steady state to infinity? Guys, what is S? I told you in the first class. No, my question, no. My question, why we say S goes to 0, you get the final value of the function. Why S goes to 0? I don't say S to 1. Why don't? Yes, S is equal to I omega, remember? This is simple explanation. When I say S goes 0, means frequency to 0, means oscillations goes to 0. Oscillation goes to 0. There is no oscillation. There is no transient. So you have the DC behavior or DC gain. We say DC gain. I'm going to introduce to later. DC gain means put the S is 0. Okay. means that there is no frequency, so you have a steady state. This is simple explanation of why S goes to 0. Okay. Being said, now I can say I have E of S. I have E of S. So you can use in this course and after graduation as a control engineer controlling a linear system. So ESS, steady state error signal, and time equals to limit of S E of S. But we calculated E of S. Gonna be a limit of S X of S 1 plus open loop transfer function when S goes to 0. Bingo. This is how we calculate the drop from block diagram or transfer function. So I'm going to change the color of this, the color of G, to red, to emphasize that you have to put open loop transfer function here, G, not closed loop. I'm writing here, open loop transfer function. Please do it at your notes. Okay? This is how we calculate the steady state value of the error signal in the control systems. Yeah. Your voice is very mumbling. I cannot hear it actually. Yeah. Okay. Mm-hmm. Yes. This as you mean? This as? Yes, obviously, because this is based on the theory. Okay? Okay. So let's back to our problem, to our example. Here we go. Okay? I'm plotting here. So here we go. Be very sharp today because I'm going to examine you. Tau, theta. This is open loop transfer function that we calculated, omega n squared over s squared. This is E. So, and theta over tau, closed loop, is omega n squared in s squared plus omega n squared. You see there's a difference between G and closed loop. See that? Huh? So ESS for this pendulum gonna be a limit of S X of S 1 plus G of S, S goes to 0 as we graphed. Now you know what? I'm gonna say, you know what guys? I'm gonna say the input to the system, to the pendulum, is this. What is this? I taught you. I want that you tell me. Delta T minus T naught. Delay impulse. Delayed impulse. This is delayed impulse. So if I want to plot it here, this is impulse. This is impulse. And this is delayed impulse. And here is T naught. We know that. So this is tau of T, but we are in the S. So tau of the S gonna be how much? What is the Laplace of the impulse? Look at the tables. Look at the table I gave you. Yeah. It is E minus S. Why? Because I told you this. if you have a given function of f of s, okay, so the Laplace of ft minus t naught is e minus st naught f of s. Remember, you have in your notes for delayed system. So you're right. Delta is 1, but it's delayed. So your t naught is 1. So suppose that it is equals this delta t minus 1. Your t naught is 1. So minus s and in 1. So it is e minus e to the power of minus s. Everybody understand, or do you want to explain that again? Yes? Okay. That's it. So now I'm going to calculate that. So it's going to be limit of s. Your input is x of tau of s. Your input tau of s is e minus s divided by 1 plus g. Your open loop transfer function is omega n squared over s squared when s goes to 0. Put s0, this is 1. S0, you can write like this. It's going to be s cubed s squared plus omega n squared when s goes to 0. So this is 0. Steady state error signal is 0. Bear with me, I'm not done. Because your answer is wrong. That's why I'm told you that be sharp today. Why? Can I go to the next page? Can I go? Okay, guys. This is what I plotted. All of you look at here. I said the input to the system is this impulse, huge force. Here is 1 second. And based on what we calculated from final value theorem, it says that the pendulum gonna behave like this. Because the steady state error signal is 0, it shows to us. That's right. The output, this is the output angle. This is the input. This is this is input. Impulse. Output follows the input finally. That's right. But is this true? No. Now I want to look at the original system before going to the math. What is that? Look at here and let me know why the answer is wrong. Why? Guys, I don't care if you don't learn control from my class. I care that when you look at differential equation, I taught you 10 times to translate the left-hand side and the right-hand side. What is the left-hand side of this system? So, on the other hand, if I say there is no input to the system, this is our pendulum problem, that's right? Yes? This is our pendulum problem, right? This. Yes? So how the system behaves in the pendulum? Stable, unstable, or marginally stable? I taught you. Means physically oscillates forever. So we are now smart. We say, hey, I don't care what's the input. Your system, even after impulse, gonna experience this, but then oscillates forever. So the error signal never goes to 0. See what I'm saying? You see, you are as a graduate of mechanical engineering. When you look at differential equation, you have to understand the nature of the system dynamics. See what I'm saying? So let's go find mathematically why this is not valid. I'm going to teach in the Ross stability criteria on March, mid-March, hopefully or end of March. Okay, so look at here, guys. Theta over tau was omega n square s square plus omega n square, or theta of s is tau of s omega n square s square plus omega n square. But what is tau of s we derive together? You tell me. E minus s, delayed impulse. E minus s omega n square s square plus omega n. Because at the end of the day, we're going to find theta in time domain. So guys, I told you, you cannot solve this differential equation when here is the impulse, because you cannot solve the unknown. So we got help from Laplace transform. So we say we shifted everything from time by Laplace to frequency. Bingo, here we go. Then if I want to find again in time domain final answer, what you're gonna do? You're gonna put Laplace inverse. Laplace inverse. So what I'm gonna do, I'm gonna apply Laplace inverse to the both sides of the equations. So theta of s is gonna be theta of t Laplace inverse of omega n square e minus s square plus omega n square. When you are done, let me know that I can move to the next page. Can I go? Okay, so theta of t gonna be Laplace inverse of e minus s omega n square. But we know that from I taught you previously that what are the poles of this system? Remember? Poles of this system. So S or S1 and 2, if you make it 0, gonna be plus minus I omega n. Remember? A pair of pure, what? Pure poles. Remember? Marginal stable system. Plus I omega n minus I omega n. These are the poles of the system. Yes, everyone? So you can decompose like this. S minus I omega n in S from high school. I omega n. Because if you multiply this, you're going to get this. Everyone agree? Yes or no? So I can take this out. E minus S for now. Laplace of omega n square in S minus I omega n in S plus I omega n. Then you can write this like that. Laplace inverse of, this is not the correct way, but I'm doing to avoid confusion, okay? A S plus I omega n plus B S minus I omega n. You know that from high school you can decompose like that. I don't care about A and B because it's a constant number. Okay? Now I'm going to re-enter that here. See? Laplace inverse of A E minus S plus I omega n plus B E minus S minus I omega n. Okay. Guys, let me know which function gives such a Laplace transform. Go and look at the table I taught you in the Laplace. I want that you go and find it. Which function in time gives you such a Laplace? This Laplace. 1 over S plus A or minus A. Which function? I want that you go and find it. What? Yeah, you mean exponential. Minus AT. Plus minus AT, that's right. Gives you this. Right? Minus gives you plus, plus gives you minus. That's right, exponential term. So, but we have also minus E minus this. What does this mean? I just told you. Yes, delay, that's right. So, on the other hand, you're going to have this plus minus A T minus T naught. See what I'm saying? When you apply Laplace inverse to go back to the time, so you go ahead. But because this is T naught is 1, so here you're going to have E plus minus A T minus 1. See what I'm saying? Yes? But your A is I omega n minus I omega n. So what you're going to do is this. You're going to be A, E. So this is plus. Here you're going to be minus. Minus I omega n. But because of this, it's going to be T minus 1. So it delayed. See what I'm saying? Delayed. Everybody understand this? Yes? Plus B minus. So this minus gives you plus. E plus I omega n. Again, the delay is here. T minus 1. But if you go back to the class 1 or class 2 that I respect the sequence of the course I'm teaching, I taught you about Euler series, Euler formula. Remember, that is cosine theta plus minus I sine theta. I taught you this Euler or Euler formula. Remember? So now I'm going to use to make these two. When you are done, let me know. I can go ahead. Okay. So, being said, angle theta gonna be A cosine, this is your theta. I mean that your parameter B. Cosine omega n T minus 1. And this is minus or plus, minus. Minus I sine omega n T minus 1. When you say this, means delayed. Mathematics means delayed. Plus B. B is plus. We're going to take this. cosine omega n t minus 1 delayed plus I sine omega n t minus 1. And as we did previously, you can do this a plus b cosine omega n t minus 1 means delay plus I a minus b or minus a plus b, just a is here, sine omega n t minus 1 means delayed harmonic response. So, and you know that we previously did, you can write this as d sine omega n t minus 1. Remember that we did this from trigonometry of high school, minus phi. Remember? So it says that if this is your pendulum, and we draw it by Laplace and then to inverse Laplace. Okay, theta t. If there is 1, 2, 3, 4, if you have a impulse, delayed impulse to this, your thing gonna be again here 0, experience the impulse, and then gonna start to oscillate forever. And this is the mathematical proof. And this is the delay 1. See what I'm saying? So that's why the final value theorem is not valid for a marginally stable system, because there is no steady state value, guys. Do you see steady state value? No, it's oscillating forever. It never settles down. This is the take-home message. Your system must settle down like this, or like this, or like this. Final value theorem, its name is on that, steady state. But there's no steady state. It's going to oscillate forever. See what I'm saying? So that's why you see by the delayed impulse, when your pendulum gonna oscillate, when you are done, let me know. Okay. So when you're plus minus, I'm putting this here. And this is input to the system, means delayed impulse. So as I told you, the pendulum has double integrator inside. If you want to remove that forever oscillation, okay, already has this. Only you need to add D controller here. D controller means S. I taught you. I'm gonna teach you eventually. And this is gonna be, I'm gonna say PD, proportional D. So the controller is gonna be like this: KP plus KDS. This is gonna be controller. Put it here. This is gonna your system like this. I'm gonna teach why eventually. Just accept from me now. Gonna experience, and then gonna be this. See what I'm saying? And your functions controlling here is the design here. There we go. Proportional derivative. D gives you S. And your plant already has, open loop has integrated. Clear, everybody? Yes? Let me go and simulate whatever I called in MATLAB. I'm going to send it by Canvas today. So what I'm going to do in MATLAB, if this is your pendulum, I'm going to show start system from the rest when the angle is 0 without an input. Then I'm going to apply delayed impulse at 1 second, say 2 seconds, t minus 2. And you're going to see when there is no input to the system going to remain here. But when I apply the delayed impulse, it's going to do this exactly as we derived. Okay? Let's do this. Oh. Okay. Oh my God. Okay. Let's hold that it comes up. Let me. So. Okay, let me. Okay, so okay, so I'm gonna define a new pendulum impulse. I'm gonna by the canvas. I'm gonna have 4 state variable. Then I'm gonna say this is one. This is without any. So this is without any impulse as input. Now I'm gonna do 3, 4, 4. This is gonna be 3. I'm gonna add delayed impulse u, but I have to define it here, guys. U put in if. I say if t greater than 1.9 and t is smaller than 2 seconds, put u a large value of 20, else u is 0. And see guys, and this is double. We write and like this in MATLAB. Okay, we write and like this. So for just 1 millisecond, no, this is yeah 9. Only for 1 millisecond I'm gonna apply a huge torque to the system u. You see that? This is impulse. Simply I introduce impulse here. But I don't want to have disturbance. Okay, this is omega n. Let me double check. So, and I have to multiply by omega n square here. See, because this is what we derived. Look at here. Omega n square tau. Let me name tau to be consistent what I taught in tau. Tau. Okay. Now I have to save it. What? With this name, impulse. So impulse. Here we go. So we don't need this. So let me double check everything. 4 omega n is 5 is 1 millisecond. 20 no. So why I multiply by omega n square? Look at here, guys. Because of this. See? Do you see this? Yes? Exactly that we did previously. Can you hear me, guys? Okay. Now let me go to solvers. For solver, I'm moving from here, putting here for new solver. For 20-second, let's put 10. So this is 1 millisecond. So, and the name of this that you have to call is this. Now you know how to work with the OT, that's right. So I said that I'm gonna put initial conditions 0 and 0. The first two for there is no input. The second is for input. Okay. This is for the input, M3 and M4, and this is for M2 and M1. So, and I'm gonna plot M3. Okay. I'm just putting this as comments because I don't want to plot it yet. I'm gonna make a movie. I'm gonna see solver impulse and solver impulse. Okay, here we go. This is the angle of without an input, angle of with input. Okay, and this is gonna be again theta degree. Here we go. Let me first debug it. What's wrong? Oh, fine. Okay. There we go. Oops, what happened? Everything's right, right? Why is not showing? M3, that's right, and this is M1. Okay. And this is 10 seconds, 0, 0. Why it shows 0? Guys. Guys, please mute your microphone, please, speaker. This is M3. Just make it big. Oh, it must show. Conpend impulse. Conpend impulse. Here is this 4-on-1. T 2.1 is 10 seconds. What's wrong? OD 4500. No, here, here it's at. Oh, it's calling. The problem is I don't know why it's not plotting third column. 0. Let me put this 1. Oh, oh, okay. That works. Okay. But it doesn't, it must have go with the 0 even. Let me put very small because of accuracy in the numbers. Let me see. Now it still shows good. Okay. So it's bizarre because when I put 0 must works. Okay. This is almost 0. See what I'm saying? This is almost 0. Here we go. Now showing. Okay. Guys, so I put to 99 1 millisecond. Okay. See, 1 millisecond. At 2, no, it doesn't take that, so I have to increase that. 0.1. Now it's a huge impulse in a short period of time. Okay. Okay, now it shows exactly at 2. See what I'm saying? So you see that without any input, so it is 0, remains stationary, doesn't move. But when I apply with delayed impulse, it's gonna oscillate forward, as we derive mathematically. Goes to see 600 degree, backs to the 800 degree. Okay, so I have to just make it small to make it 10, to make it reasonable, guys. See, to 300 to minus 300, even that is high value. I don't know, say to 3. Here we go. Understand, guys? Now you can change the delay. Delay you can put at the 5. See, I'm gonna say 4 to 5-1. There we go. If I do that, oh, now we have to change the initial conditions again. Let me put this clear all. Here we go. See, delay happens at 5 seconds. See, and then oscillates forever. Now, let me see now if it works. No, actually, it's sensitive to. Okay, this is almost 0, by the way. There we go. Okay, so they started from almost 0. So this is the angle at the starting, guys. Look at here. See, the angle is starting 0 to the power of minus 6. So because of some numerical issues, I have to put almost 0 here. See what I'm saying? Yes? So, yes. And let me see. Yeah. Now I can make the simulations. And T, I'm gonna put con 1, 3, 3, subject to delay, 3, 3. So let us see if it runs simulation. What? Three, 3. What is the exceed? XV. Oh, these are moving pendulum, guys. Yeah, so I cannot simulate this for that. I'm sorry. I think these are moving pendulum. Okay, forget about this. Okay. Yeah, with the disturbance. Okay, I cannot do that. So this is take a message, okay? We showed in MATLAB, okay, exactly as we derived in theory. Here we go. See? Even you can start from, let me try this, 8 seconds. It cannot remain there. And hopefully, yeah. But you have to play with the initial conditions. There we go. Oh, it goes to the end, so you have to play a little bit. Don't go to the 8. Makes a problem. Just keep it as 4. Okay? Because this is not very accurate. This is not accurate impulse. This is just approximate impulse that we are plotting. Oh. Oh. What is this? Okay. There we go. Okay? See what I'm saying? But in the Simulink, we can apply this exact impulse. This. I'm going to show how to do in the Simulink. Exact delayed impulse eventually. Okay? Clear?